All right, friends, happy Monday. Welcome back. This is exam week, so please pay attention to the exam dates that are listed on the syllabus when the exams open at the testing center. The exams are multiple choice. The exam is multiple choice. It is not timed. There will be somewhere between 25 and 35 questions. Yeah, and you should expect about the level of difficulty of the practice exam. Format, of course, will be different because it will be multiple choice. You may write on the exam. You may also attach scratch paper to the exam. I, in fact, recommend stapling your scratch paper to the exam before you leave in case you want to come inspect the exam in my office and look at the work that you did. If they tell you you can't do that, you simply reply that I said you could, and they will let you. All right, well, we've been talking about these intermolecular forces or non-covalent interactions. We've sort of described 4 different situations in which you have a not uniform distribution of charge in a molecule. Although I suppose, the most intense the most intense concentration of charge is just the full ion. It's a point charge. Then you have dipoles, quadrupoles, and then what we called induced dipoles. This is a weird concept, but it's related to the fact that when 2 molecules approach each other closely, because their electron clouds repel, there's an energetic incentive for the electron clouds on both molecules to move in a correlated fashion, meaning if they lean such that this side is electron poor, the electron cloud on the other molecule will correspondingly lean so this side is electron rich, and then you have a temporary attractive interaction. This isn't a permanent interaction, and it shifts back and forth from moment to moment, but overall, because the electron clouds on one molecule are correlated with movement of electrons on the other molecule, you've got this weak attractive interaction. Now, a couple of things we need to say about the strength of these interactions. Pretty simple principles here. The first is that opposite charges attract and like charges repel. So these interactions can be both attractive and repulsive depending on the situation. And then the second, or maybe third, I guess these are all part of the same principle. The second basic principle is that proximity or distance matters. Closer is stronger. And if you think back to physics class where you learned about Coulomb's law, there's for the force, it's an r squared in the denominator. For energy, it's just r in the denominator. The bigger the distance between 2 charges, the weaker the interaction. That's true for all of these intermolecular forces or non-covalent interactions. The closer 2 dipoles are together, for example, the stronger the interaction. In terms of the closer a cation and a quadrupole or a benzene ring are, the stronger the interaction. For induced dipoles, we're going to add one more consideration to this issue of proximity, and that is what I'm going to call contact surface area. The induced dipole interaction is extremely short range. Molecules have to be really close together in order for this to happen, and the more extended surface-to-surface contact the molecules have together, the stronger the interaction is. And we're going to see that matter when we start talking about why fats are solids but oils are liquids. Okay, with that in mind, I want to just take, with those ideas of strength of interactions in mind, we're going to go through some observations that you see in your everyday life, in the kitchen and in the world around you, and we're going to tease out sort of what's really going on at the molecular level. So we started to do this with why does salt dissolve in water? And then if salt dissolves in water, why does oil not? So in order to understand why anything happens in chemistry and biochemistry, you have to have a decent understanding of free energy, which you remember as delta G equals delta H minus T delta S. We got some Gen Chem PTSD going on there as I wrote an equation on the board. It's not as bad as you think. Enthalpy refers to changes in the strength of bonds, for sure, and also the strength of non-covalent interactions. So for a process, enthalpy is going to be negative or favorable if the bonds we make or the non-covalent interactions we make are stronger or more stable than the ones we lost. Okay? In energy, free energy enthalpy, we're always thinking about comparing your final state in a process to the previous state. So strength of bonds or non-covalent interactions gained in a process versus lost. And then delta S is entropy. And in the case of entropy, what we're really worried about is disorder. Disorder gained or lost. Entropy is really a probability thing. It just so happens there's way more ways to be disorganized than there are to be organized. And so it's more likely for things to become more disorganized in a process. So we can use these two ideas, interactions or bonds, how strong they are before a process versus after, and then disorder, how ordered were we before versus after, to get a sense for whether a process should be favorable or not. If delta G is negative, the process is going to be favorable. Another word for that is spontaneous. And then if delta G is positive, it's going to be unfavorable. So with that in mind, let's consider salt before it dissolves in water. You have an extended, and I think you've probably seen something like this in a model that somebody brought to class, sort of this cubic lattice of sodium and chlorine ions. Do I have to draw the full cube? Actually, watch this, the magic of copy and paste. Don't you hate me right now? And then we will just copy that, a little bit of offset. Another little bit of offset. I hate me, so let's just, I have a decent sense of self-worth, but cubic lattice. So a very ordered lattice where the salt or the sodium and chloride ions are very close to each other. And then you have water. What do you suppose is going on in water before the salt dissolves? Hydrogen bonding, which is just a particular kind of dipole-dipole interaction, right? So in crystalline salt, you've got very strong, tight ion-ion interactions. And then in water, you've got hydrogen bonding, or in other words, dipole-dipole interactions. Okay, that's fine. So in terms of strength of interactions, would you say these, we would probably say that these ion-ion interactions are strong. And we'd also probably say that the dipole-dipole interactions are strong, but perhaps not quite as strong as the ion-ion interactions. How about disorder? What do you think about the crystalline lattice? Relatively ordered, right? If you know where one sodium ion is, you know where every other atom is in the structure. That's a lot of order. Water, considerably less ordered. It's a liquid. The water molecules can shift around each other without losing hydrogen bonds. Okay, so now let's think about after the process. We'll call it an equilibrium process. We'll call it dissolving. Let's sort of draw what happens after dissolving. So you have a sodium ion. It is no longer close to any other chloride or sodium ions. You know where one sodium ion is. You know nothing else other than where that sodium ion is. You might also know that the water molecules in the immediate vicinity of the sodium ion are going to be oriented with the oxygens a little bit towards the sodium. Why do you suppose that is? Yeah, this is now an ion-dipole interaction. And you've got the negative ends of the water dipoles facing the sodium dipoles, facing the sodium ion, right? So up here in the crystalline lattice, we had one sodium surrounded by, can't count, 6, is it? Or some number of chloride ions. Now we've replaced those surrounding chloride ions with water. All right? And we could say the same for each and every chloride ion that is dissolved. In this case, probably you would want the positive end of the dipole oriented towards chloride. And in fact, you might, in addition to these just ion-dipole interactions, there may be some kind of hydrogen bond where some water molecules have their protons oriented towards the chloride. I'll draw both options. All right? So the question we have to consider then, we replace the tight ion-ion interactions with ion-dipole interactions. And some of the water molecules in the immediate vicinity of the ions are going to be interacting with the ion itself and not with other water molecules. So we're going to lose some ion-ion interactions. We're going to lose some hydrogen bonding interactions among water molecules. We're going to gain a lot of ion-dipole interactions. All right? So you know from experience that the dissolving process, delta G, is negative because it happens. Sure. Right. For Cl minus, I drew it this way to indicate that there are two ways that you could conceivably imagine water interacting with chloride. You could imagine water orienting itself so that the positive end of the dipole of water is oriented towards chloride, or you could imagine some kind of hydrogen bonding where it's the proton that's oriented towards chloride. I'm showing both options. There's not a right answer. Hydrogen bonding can't happen with the positive over here because the hydrogens are at the positive end of the dipole, and that would be repulsive. Yep. Right, so you know this process happens because delta G is negative. Sure.
So some of these next edge nitrogen hydrogen bonds happen to be nitrogen, oxygen, and fluorine.
Okay. Hydrogen bonding, when it says it happens with nitrogen, oxygen, and fluorine, what they're talking about is the thing that the hydrogen is attached to in order for that bond to be polarized enough to engage in hydrogen bonding. They weren't talking about the other partner that interacts with it, right? So the other partner that interacts with the hydrogen bond with the hydrogen end of a hydrogen bond needs to be something that's negatively charged. And if it were neutral, it would help if it were an electronegative atom so that there could be a delta minus on it. Yeah. Okay. So if we consider, again, delta G is negative for this process, why is that? Well, let's think about enthalpy. You can see there's two ways for delta G to be negative. Either enthalpy can be negative, or entropy can be positive, or both, right? We're not interested in what the exact number is here. We just want to think about trends. For this process, what we would be saying in terms of enthalpy, if enthalpy is negative, that means the interactions we gain are about as strong or perhaps stronger than the interactions we lose, okay? Can you see how replacing some ion-ion interactions with tons of ion-dipole interactions might be favorable? Then in terms of entropy, we've gained a lot of disorder by going from the crystal and lattice to just be floating around in water. So this is why dissolving salt in water, which is okay but somewhat boring, is why it's favorable, why it can happen. Even though you've been told that ion-ion interactions or ionic bonds are strong. Strength is always relative. When you want to determine if a process happens, draw out what it's like before, draw out what it's like after, and then compare the two situations. When people say that ionic bonds are strong, they're talking about relative to taking two ions that are close together and then separating them in a vacuum to infinite distance. Yep, you got it, that's strong. And that's why actually you put salt on a hot plate in the kitchen, try to melt it, you actually probably aren't going to be able to do it. The melting point of sodium chloride is really high. But put it in water, no problem. Okay, it's always relative to what? Yes? Explain why the ion-dipole interaction is more favorable than the ion-ion interaction. Per pair of, if you want to consider a comparison, a sodium ion to a chloride ion versus one sodium ion to a water molecule, you're right, it's not more favorable. But what we are likely doing, I've only shown you a few of these, but each sodium ion is probably surrounded by, I'm going to throw out a number, 10 to 12 water molecules. And so you're replacing a smaller amount of stronger interactions with a larger amount of weaker interactions. Overall, the balance is probably favorable. Somebody's actually done that math. I don't know what the answer is, but you combine that consideration with the entropy consideration, and it's favorable in the forward direction. Yep. Okay. Good. Yeah. Right, good. So when entropy is, when delta S is positive, that means more disorder. When delta S is negative, that means less disorder. Notice that because in the equation you've got minus T delta S, a positive entropy leads to a favorable change in free energy. Yeah. All right, so salt dissolves in water. That's great. Now let's deal with oil and water. Which you know doesn't necessarily happen. So to talk about this in more detail, we need to actually see what oil looks like. So I told you, I've already given you a preview of scary biomolecules, which I drew with angry faces. This is maybe going to be your first scary biomolecule without an angry face. What I'm going to draw for you now is a triglyceride. You've probably heard of that if you've ever had a blood test and they looked at the concentration of triglycerides in your blood. A triglyceride is this 3-carbon alcohol where each of the OH groups is tied up in an ester functional group with a long chain carboxylic acid. And the length of these carboxylic acids can be anywhere from 12 to 20 carbons. I'm just going to do 2, 4, 6, 8, 10, 12, 14, 16, 18. All right, 18 carbons. I don't want to do that again, but here we go. 2, 4, 6, 10, 12, 14, 16, 18. And then we'll just do another one. 2, 4, 6, 8, 10, 12, 14, 16, 18. All right, so this is a triglyceride. Now, don't worry about the fact that I've called this an oil. What I've actually drawn here is more of a fat than an oil, but the point is that you have a lot of bonds here that are relatively nonpolar, no electronegativity differences. Therefore, probably this one is going to be fairly nonpolar and not very good, in other words, not very good at ion dipole or dipole-dipole types of interactions. Okay? So if you were to dissolve this molecule in water, unlike what you've seen before, where water molecules can surround the molecule very nicely and interact with it, here the water molecules would have to be around this fat molecule, but they couldn't hydrogen bond with it. Okay, some of you are saying, well, couldn't they hydrogen bond with this group and this group and this group and this group? Fine, yes they do, but certainly not with this portion. Question?
So is that why it's nonpolar, is because you can't bond with that rest of that portion?
It's nonpolar because all of the carbon-carbon and carbon-hydrogen bonds have similar electronegativities, so there's simply the dipoles are really, really weak. There's not very big delta pluses or delta minuses on anything in those long hydrocarbon chains, which means that the long hydrocarbon chains can't really hydrogen bond well with water, and they can't really interact with ions. All right? So let's actually sort of zoom in and consider what would happen. Let's see. Well, here's our... drawing this out in a lot of detail is going to be sort of a pain, but we just as well do it. So let's think about what's happening on oil and water, before we mix them. We're going to zoom in on the nonpolar hydrocarbon tail of an oil molecule. And I'm just going to show a couple of zigzags here. And we'll draw in some carbon-hydrogen bonds. Because the triglyceride is not good at ion dipole or ion-ion type of interactions, the best it can do is one of these van der Waals interactions or induced dipole interactions. That is, these bonds are not very polarized, there's not a very big buildup of positive or negative charge in either direction, but as the hydrocarbon chains either within the same oil molecule or on adjacent oil molecules approach each other, you can get these temporary limited induced dipole interactions where, as we've discussed, the electron clouds on both molecules correlate with each other to create a temporary attractive interaction. You've called this before a van der Waals interaction, but if you like, I mean, there's about the same words in either case, but an induced dipole / induced dipole interaction. All right, or dispersion interactions. Now, those interactions overall are weak relative to, say, an ion-ion interaction. Nevertheless, they're strong enough to keep oil in the liquid phase, right? And so their added nature is overall enough to observe. We've seen water molecules again, as we talked about with the in the case of salt dissolving. You know, an individual water molecule is going to be hydrogen bound to a lot of other water molecules. So if we think about, you know, the enthalpy and entropy considerations, before we try to mix oil and water, you've got van der Waals interactions in the oil, you've got hydrogen bonding in the water, and especially in the case of water, you've got a lot of entropy going on because each water molecule can switch to hydrogen bond with another water molecule without moving very much. So there's a huge amount of disorder. You can also move the positions of water molecules without changing the hydrogen bonding very much. All right, now let's consider what would happen if we were to dissolve a single oil molecule in water, okay? So I'm gonna just copy one of these oil molecules. Let me ask you this, is water capable of van der Waals interactions? Sure, every molecule is, right? If you have electrons, you're capable of van der Waals interactions. So if we surround this hydrocarbon, or in this case, this oil molecule with water, we probably aren't losing too much in terms of van der Waals interactions. Does that make sense? Okay, but let's think about what happens to the water. I told you that the hydrocarbon can't hydrogen bond. So we're not going to do anything here where we try to show that there's some kind of hydrogen bonding interaction with a water molecule. Instead, if you think about this, a water molecule that's immediately adjacent to the hydrocarbon has a whole space nearby it where it used to be able to hydrogen bond with something and now it can't, because the thing that's taken up space nearby is not a water molecule, is not capable of hydrogen bonding. So each water molecule in the immediate vicinity of this hydrocarbon is not hydrogen bonding as much as it's capable of. What that does is that makes the remaining hydrogen bonds between water molecules in this immediate vicinity shorter and stronger to compensate. And so you end up with, and stronger bonds, shorter and stronger bonds mean that the water molecules in the immediate vicinity of the hydrocarbon are no longer moving around quite as much. This is going to take me a while to do, so copy and paste isn't working for me so much here. Okay, so the point is that in order to accommodate the hydrocarbon, the water molecules that immediately surround the hydrocarbon, we call that the solvent shell. Those water molecules have to get closer to each other and they have to slow down, almost as though, and here we're not somehow completing the chain, oh well. Maybe that one's hydrogen bound twice, who cares? So the water molecules in the immediate vicinity of the hydrocarbon or the solvent shell have stronger hydrogen bonds with each other, but fewer hydrogen bonds, because they used to be able to hydrogen bond with the stuff that was in here. Now it's something that can't hydrogen bond with it. Does that make sense? No, not particularly. Up here, perhaps, a water molecule, if you think about it, each oxygen has 2 lone pairs and 2 hydrogens. So each water molecule can conceivably engage in 4 different hydrogen bonds. 2 as a hydrogen bond acceptor, and 2 as a hydrogen bond donor, right? Whereas here, at best, each water molecule is interacting with maybe two other water molecules. So we've lost some interactions, and the fact that the remaining interactions get a little bit tighter mean that we lose a lot of disorder. Disorder decreases, or in other words, for this process, entropy is negative, because the water molecules immediately surrounding the hydrocarbon slow down and almost become like a layer of ice. The point is, if you were to dissolve a hydrocarbon in water, you would force the water molecules immediately surrounding the hydrocarbon to be rigid, ice-like, and lose entropy. Okay? And overall, that means that this process is unfavorable. Delta G is greater than 0. Remember, if delta S is less than 0, and delta G equals delta H minus T delta S, then you can see how a negative number here could ultimately lead to a positive delta G. All right? Yeah?
Delta H in this case, would it be, so you're getting like constant fractions even though you have Tesla, so it would be.
What about delta H for this case? You can actually make the measurement, and I'm not totally sure what it is. In terms of van der Waals interactions, it's probably neutral, because water's capable of that too. In terms of hydrogen bonding, it's probably unfavorable, because you're losing, you know, if we just, this is crude and back of the envelope calculations, but we said each water molecule can have 4 hydrogen bonds up here, maybe 2 here. You've lost a lot of hydrogen bonds. So at least my prediction is the delta H is also positive for this process. Yeah.
Is the water and the hydrocarbon, is that oil?
The water here is just, this is showing you, what we've intended to show you here is what would happen if the oil dissolved in water. These are water molecules that immediately surround the oil.
So hydrocarbon, oil, and the water.
Yeah. Yep. Yes?
So yeah, I understand that it holds it tighter, which decreases the disorder.
Yeah.
But when you have fewer hydrogen bonds, wouldn't that increase the disorder? Don't you want things bonded more?
That's a great question. Does more hydrogen bonds lead to a decrease in order? In liquid water, apparently not, because you can, this is just a static picture, but this water molecule doesn't stay hydrogen bound to this one. They're trading all the time. And the point is that if they're around the oil molecule, they have to slow down and actually not trade partners all the time. And so there's another issue of how rapidly you can exchange one interaction for another that's at play here in terms of the entropy. One interesting prediction that you might make here, I told you that overall this process is unfavorable, because if you did dissolve the oil in water, it would lead to a loss in entropy. So we might say that this process is entropically favored. But look back at the delta H minus T delta S for free energy. If I told you that entropy was negative, what would you predict for delta G if I lowered the temperature? What should that do to the impact of entropy? This number's negative overall, this number's positive, but if you decrease temperature, it should get less positive, right? That leads to an interesting prediction, which is the solubility of oil in water should actually increase with lower temperature. And you can actually verify that. That's actually true. That nonpolar compounds get more soluble in water as you decrease the temperature. All right. So if you wanted to get oil and water to mix, probably, I don't know, heating them up might not be the best solution, right? In terms of cooking, what do you do to solve this problem? Because you often need to create delicious baked goods, both oil and water, in your recipe. What do you do to facilitate this process? Anybody know? Go ahead. Say that again. You used the right word. It's a good word, yeah. Emulsion, right? Yeah, you use something that's called an emulsifier, which in a lot of recipes is eggs, right? Yeah. The emulsifier has portions of it that it's a molecule that has portions that are okay interacting with oil and other portions that are okay interacting with water. There's another kind of emulsifier that you have a lot of experience with, and it is soap, right? So let's talk about soap and how soap allows oil to dissolve in water. So to know some things about soap, it's helpful to know some history. It turns out that making soap used to involve taking the oil molecule and subjecting it to highly basic conditions. So this was frontier organic chemistry 200 years ago, you would take the fat molecule or oil molecule, normally animal fat, so this is a molecule you would find in animal fat, and you would use something called lye, which you can get from ashes, and that's really potassium hydroxide. This reaction you'll learn about in 352. It's called saponification, which probably, I think, literally just means soap making. This hydrolyzes these ester bonds between the 3-carbon alcohol and each of these long chain hydrocarbons. It releases the 3-carbon alcohol, which happens to be called glycerol. In most cases, that wasn't isolated. What was left over, though, was a carboxylic acid in its conjugate base form, 2, 4, 6, 8, 10, 12, 14, 16, 18. And you would have 3 of these. And now you have a molecule that has what we're going to call amphipathic character. Amphi meaning both, pathic meaning love. This molecule loves 2 different conditions. It has a non-polar tail, which does not like to interact with water for reasons we have just discussed, but you have a polar head group that is perfectly fine interacting with water because it is capable of what kind of interactions? Hydrogen bonding, yes. What else? Ion dipole interactions, yes. Okay? So now we have a molecule that can do 2 things. And what you tend to see for these molecules is that they can adjust themselves to accommodate their environment. So you put the non-polar, and by the way, this is called a fatty acid, which seems, I guess, somewhat insulting, but that's actually what they call it in biochemistry. It's derived from a fat or oil. These have a polar head group and a non-polar tail. I'm going to use the color red for the electron-rich polar head group, and we'll use the color gray for the non-polar tail that, because of this entropy issue that we talked about above, doesn't like to interact with water. Let me just pause and tell you that what we talked about above, that oil not dissolving in water, is called the hydrophobic effect. And what I want you to understand is that the hydrocarbon tail is not afraid of water, and the hydrocarbon tail doesn't dissolve in water, not because these van der Waals interactions are so strong, but because if it did dissolve in water, you would have a massive decrease in entropy due to the freezing out of the water molecules immediately surrounding the nonpolar tail. All right? But the fatty acid has no such problems because it's got this polar head group. So imagine what happens in water. For this, I will copy and paste. Don't worry necessarily about copying this down. You can get it in the notes that are going to be posted online. But what will happen, molecules of this kind can do something called self-assemble in the presence of water. They can arrange themselves so that the nonpolar tails are actually protected from water, whereas the polar head groups, which are perfectly fine interacting with water, are exposed to the water. All right? And you can see, just based on sort of the shape of these molecules, how if you arrange them sort of in this spherical pattern, we got about something of a semicircle there. Paste. Look at that excellent animation. Isn't that great? What you have is the formation of what's called a micelle. And this is a supramolecular structure. That means association of more than one molecule together. Outside, which I'm going to represent just by writing water, outside the micelle, you have water molecules that are interacting perfectly favorably with the polar head groups. And there's no such entropy issues here because they can trade off and switch very easily, unlike in the case where the nonpolar tails are exposed to water. But the interior of this micelle is nonpolar, all right? So if you are washing your hands and your hands are covered with bacon grease, which is a solid at room temperature, we'll also talk about why that is. The micelles in the soap, as you lather your hands, are going to be able to accommodate nonpolar molecules in here. This is like a little capsule of oil that's been surrounded by a water-soluble group. And so it's very easy for your oil molecule to fit in the inside of this micelle, where it becomes magically water-soluble because it's being carried away in a capsule that's specifically made for that purpose. Okay? This happens every time you wash your hands. This is how soap works. Of course, soap technology has evolved a lot from the days when we were just using animal fat and hydrolyzing it. There's a lot of different varieties of soap molecules. These types of molecules are often called surfactants or detergents. All of them have this basic characteristic of being amphipathic, meaning they have a portion that can interact with water and a portion that is non-polar. I will just draw one of these for you. Let's see. If you look at your bottle, if you read your bottle of shampoo in the shower, which you don't have to confess if you do that. I have definitely been bored enough while showering that I have read a shampoo bottle. You'll see sometimes this word sodium laureth sulfate. What this is the polar head group is not a carboxylic acid. Instead, it's this group. And then there's a portion that's maybe 2 or 3 of these 2 carbon plus oxygen spacers. And then at the end, there's a 2, 4, 6, 8, 10, 12 carbon chain. 2, 4, 6, 8, 10, 12. And you can see how even though that differs from the specific structure you saw before in our hydrolyzed animal fat, this fatty acid, if you relax your eyes a little bit, you can see the same basic structure, polar head group, and maybe that polar head group's a little bit larger because this section with the oxygens is relatively polar, and then non-polar tail. And so this is how people invent soap molecules. They put together a polar head group and a non-polar tail, and they see how well it works. And there's tons and tons and tons of these. This goes on all the time. There's a company my dad used to work for up in Salt Lake City called Sun Products that makes this type of detergent with a sulfate group at the head and then a non-polar tail all the time. All right, so soap. Let's maybe talk briefly about lipid bilayers while we're at it, because the same principle basically works. So you've seen you've seen how the animal fat is a parent compound for soaps. But the triglyceride is actually also a lovely parent compound for phospholipids in biology. One of the most important aspects of biology is this idea of compartmentalization with membranes. This allows you to separate the inside of the cell from outside of the cell, and subcellular compartments like mitochondria and nucleus from other portions of the cell. And that's really important for keeping all the chemistry going. Membranes are also what defines us relative to stuff that is not us, right? So you can take the fat molecule, and if you hydrolyze not all 3, but one of these ester bonds, I'm going to make the alcohol group go in the other direction. This is no longer a triglyceride. This is a diacylglycerol, which has, I think, some signaling properties in biochemistry. And then if you tack something even more polar on that OH group, In this case, we're going to do a phosphorus doubly bonded to an oxygen with a negative charge there, and then another oxygen here, 2 carbons, and a nitrogen, where the nitrogen is going to have a positive formal charge. This is what is called a phospholipid, and it is called, if you don't need to know what this molecule is called, but you may encounter it in your future. This is called phosphatidylcholine, and it is a lipid that is used in the membranes of eukaryotic cells. It's got a polar head group, although in this case, and I'll still use maybe, I don't know whether to use red or green or something for this polar head group. Notice that it's a neutral polar head group, but it's polar, right? You got a positive charge on it, on a negative charge on it. We call that a molecule that's polar, but is neutral because it has both positive and negative charge. We call that a Zwitterion, or if you want to pronounce it like the German word that it probably comes from, Zwitterion, and then you can feel fun, I guess. But Zwitterion is a neutral polar group that has both a positive and a negative charge in it. So there's your polar head group. And then instead of one nonpolar tail, you have 2. I want you to consider the contrast between your fatty acid and its shape versus the phospholipid that I just showed you. Notice that the phospholipid the fatty acid has sort of a conical cross section. In other words, it gets narrower the further on you go. The phospholipid has more of a cylindrical cross section or a cylindrical shape because of those 2 nonpolar tails. The conical shape of the fatty acid allows it to assemble into this micelle-like layer shape, but the cylindrical shape of the phospholipid allows it to do something different. In other words, if you line these molecules up in water in the same way that you would line up the fatty acid, they're not going to curve towards each other quite as much to make a sphere. Instead, you're going to get a layer, a monolayer, which actually, if you think about being in water, this doesn't help you too much, because you're going to be surrounded by water molecules on both sides, right? It wouldn't you're not gaining too much by having all of these lined up on the same face of this monolayer. So what does nature do? It just takes one monolayer and lines up the nonpolar side of another monolayer, and then you have your lipid bilayer. Okay? Same basic principle, but the shape of the molecule is a little bit different. So instead of a micelle, you get a bilayer. But it's still based in this idea of the hydrophobic effect. All right, well, that's all we have time for today. I will see you Wednesday.